So I'm going to try to make this a fairly painless introduction to the subject. And I have only one request, and that is if you have any question at all, please raise your hand and ask. Don't be shy. I always say that there are no dumb questions. There are only dumb answers, and I'll try not to give any. Okay, so here's what I intend to do, and I want to start by pointing out that in so-called wired networks, networks that are engineered to have clean transmission links between elements in the network, you don't have much of a channel issue. People still make semi-careers out of solving channel problems in these wired networks, but they're really pretty simple and clean and well-behaved and stable. Fortunately, that's not true of wireless channels, which are very bad for reasons that I'll get into. So I'll talk about channels in wireless networks, tell you why they're so bad that we have to study them. Then I'm going to make an important distinction. There's something called large-scale variations in wireless channels and small-scale variations. And it's an important distinction. And so I'm going to explain what the distinction is, and then I'm going to talk about each one of them in turn. The large-scale variations have to do with what's called path loss, and I'm going to spend a reasonable amount of time describing path loss and the models that are used to describe it. And then I'm going to talk about the small-scale path variations, which have to do with multipath. It has to do with the fact that in a wireless environment you have lots of scattering objects, and they produce something called multipath, and I'll talk about that for narrowband channels, which produces what we call Riceian and Rayleigh fading. And then I'll talk about broader band channels in which multipath manifests itself in a different way through dispersion or distortion of the signal, and that involves a lot of material. So in order to keep this from being a long, boring talk, and make it instead a short, boring talk, I'm probably going to stop at about this point. We'll see where we are in an hour. But I don't think if I cover all of this in one day that you're going to be able to absorb it all, especially if you're sort of new to the subject. So that's my intent, and let's see how things go. And please, again, ask me questions. All right, let's start with wired networks, and by that I mean networks that are really engineered to be fixed, stable, and well-behaved. And I'm going to include in wired networks radio, which I'll explain. So here's a typical network. These are elements. They can be routers or switches in a telephone network. The transmission links can be either, which we call the channel, by the way, can be fiber, optical fiber, which is very clean. A coaxial cable, likewise, except for sort of an attenuation with distance. And radio. By radio, I don't mean the radio we use in cellular or in wireless LANs. I mean point-to-point radio where the towers are very high, like on mountaintops or very tall towers, and they have a very clean shot from one radio tower to the next, so that basically it's free space propagation, and signals are undistorted, and the only distortion at the other end may be additive noise. So I think of that kind of a radio link, the point-to-point radio towers, as part of a wire channel. Okay, so let's see how these so-called wire channels behave. Here are two nodes or elements in the network, and they want to talk to each other. So here's the channel, and it might have repeaters in it, and the repeaters do the following thing. If we plot the log of the probability, the log of the power that's transmitted as a function of distance down the path, what you get is a linear fall of log power with distance d, and that's true in fiber or coax, or a linear decrease of power with d, with log of d in radio. Either way, it's a linear relationship where the power falls to some threshold, and the system designer says, I don't want the power to go any lower, so that's where the designer plants a repeater, which might just boost the signal or might decode it and regenerate it. But either way, what comes back out is a high power signal that again decreases in power versus D or versus log D, and then gets boosted again and so on until it gets to the node. And there's a chair, right?
Yeah, it's too close to the front.
Okay.
It's not good if you.
Your pass this chair up.
What you should do with that?
So, you can see how clean these so-called wired channels are. And now, fiber or coax, the power decays exponentially. That's why the log of P is linear with is linear with distance d. In the case of radio, power falls as 1 over d squared. And so log of P is linear with the log of d. But either way, you have this nice clean behavior, it's predictable, and you know how to engineer for it. So you can write the receive signal at the end as being just some pure gain. It's not frequency selective, it's just a number, times the original signal plus noise. Shot noise in optical fiber or thermal noise in cable and in radio. Okay, so that's the wired channel. Now, let's think about channels in wireless networks. The big difference is that in wireless networks, one or both ends of the link are not under the control of the system designer because people move about, terminals move about. And they're usually inside structures that have lots of walls, floors, objects, and so on. So you can engineer those kind of channels the way you can the nice fixed wired ones that I just talked about. There's cellular networks such as 3G, there are wireless local area networks like Wi-Fi, fixed wireless where you transmit high-speed internet from stations to homes like WiMAX. There are home networks using ultra-wideband, these are personal area networks. And there are various distributed networks that a number of you are studying here, ad hoc, mesh, sensor, cognitive radio networks. All of these have the property that one or more ends of each wireless link are in a bad place, surrounded by objects or walls or buildings, and therefore the path is both not predictable and, in particular, not very nice. So here's a rundown again of the characteristics. Low antenna heights and obstructions in the case of wireless channels. The result is that you get more path loss than you would in a nicely engineered wired network. Scatterers in the environment, which give you multipath. For narrowband signals, that results in fading. For wideband signals, in addition, you get dispersion or distortion of the signal shape. Then there's mobility. One end or the other or both can be in motion. This produces time variations. And then finally, in cellular in particular, but in wireless LANs as well, you reuse frequencies in different parts of the environment in order to get the most throughput out of your available bandwidth. And this gives rise to co-channel interference, as one transmitter transmits signals that get into the operating region of another transmitter and causes interference to their receivers. So here's a nice simple way to describe it. The received signal in this case has a constant factor that's really less than 1 and therefore represents added path loss. It's got an impulse response which has dispersion, and that's something that I'll get into later, that produces a spreading of the impulse response and therefore a spreading of the received signal, which therefore causes intersymbol interference. And also this function of impulse response versus time may itself be different from one time to the next, so it's time varying. And in addition, there's co-channel interference. I'm not going to talk at all about co-channel interference and noise. I'm really going to talk about what the channel does to create this kind of an effect instead of the very simple relationship I showed before. So, is my motivation clear? Is it clear where we're going? Questions? Okay, now I'm going to make this important distinction between large-scale and small-scale variations. Let's talk about what we mean by the response of the wireless channel. Transmitter here, receiver here, the space in between them is the channel, and the signal that's transmitted from here to here undergoes certain changes. The way we characterize that path is as the ratio of the electric field. Mainly, I think we're out of chairs, guys. Here's more faculty that came to help me out.
In trouble if they start asking questions.
Hmm?
You're in trouble if they start asking questions.
Okay, so the way we characterize the channel response is the received electric field at the receiver divided by the transmitted electric field at the transmitting end. So these are complex numbers. Let's say at a particular carrier frequency, it would just be a ratio of complex numbers, which you call little g of x. X in this case is the receiver location on the terrain. It just marks a place on the terrain that this particular receiver is at. As x changes, the response will change. Now we just do a convenient normalization. We factor g into a term capital G square root times an h of x term. The whole idea is h of x, as I'll say in a minute, is just the local average of h magnitudes. G is just the squared, the average of the squared magnitude of little g over the local spatial environment. So it represents something that we call the path gain. H therefore has the property that the squared magnitude of it averaged over the local domain is 1. So it's just a normalization for convenience. And then we can focus on this quantity G and what it depends on. So G is the locally averaged power gain, or H is the normalized complex response. And remember, this is all at a single frequency. Now let me say something about H and its statistics. It varies over local space in a way that is generally complex Gaussian. So you can write this as a complex Gaussian quantity. It has unity variance, and most of the time it has zero mean. This means that the magnitude of H is Rayleigh distributed, which is what we call Rayleigh fading.
Here the x is the dummy, it's, x, you put x here, is it just dummy variable, or it's actually a function of time?
Okay, just
Well, I didn't get the time yet, but
The x is a distance here, or the, what? It's like, h is a function of x, right?
yeah,
What is x?
H varies over the terrain. So as it moves from one x to another, it takes on a different complex value. And over many places within a local area, let's say within many wavelengths of the center, it comes from the same population of values, but it has different values that collectively are complex Gaussian, not Nakagami.
So the variation comes because, not because of the terrain itself? Or?
No. Right. The question is, does the variation come because of changes in the terrain? No. What I mean is that the terrain is kind of the same. The terrain hasn't changed between you and me. So the terrain is the same. What changes is the collection of echoes that come into the receiver because of multipath, but have different phases here than they have here, and that's what causes the variation. That's what produces h of x. There's a larger scale variation that changes G, but I'll get to that in a minute. Is everybody clear about that question and the answer? Why is X changing? Why is H changing over X? It's not because the terrain is changing. It's because of something else, which I'm coming to.
But how do you define the you said locally averaged? How do you define how big is the local area?
Okay, how do you determine how big is the local area over which you make this statistical assumption? It's kind of fuzzy. It's not well defined, but what you can say is this: over several wavelengths in all directions from a point, you have pretty much a population of values that define a statistical population. So at least over that area, you can say it's locally Rayleigh distributed. Now, you can make it a larger radius if the area doesn't change too much, if the terrain doesn't change too much as you move away from the center. But let's say the order of meters is the local area in most
So
cases.
statistically, if you change X, you somehow move to another locality.
Well, if you change X, it means your receiver is at a different spot on the terrain.
Right, but with respect to for one X, you have a local area, and you move X.
Yeah.
because you get a new area.
Right,
They might overlap.
sure. All right, so think of a starting point for a receiver. And now you want to, you're making an indoor measurement. You start right here. I say I want to compute the local gain, the local path gain to that terminal, that transmitter over there. Starting from here, I might define a circle 10 wavelengths long, right? And then use my antenna to sample it throughout different parts of that circle. So relative to that point, there's a local area. If I'd started there, then that would have been the center of my local area. In general, it doesn't matter unless you get into an extent that's so large that features in the terrain start to change. Then you're talking about a new neighborhood. So, if in fact the magnitude of H is Rayleigh distributed spatially over the spatial set that I'm sampling, then its squared magnitude is exponentially distributed, and it's got a mean value of 1. And this is just a mathematical result that you either learned or will learn.
So on this local area, you have Rayleigh distribution.
Yeah, all the samples you take over this area collectively become complex Gaussian population, so that its magnitude becomes a Rayleigh population, and its squared magnitude becomes an exponential population.
So why did you write mostly zero mean?
What, Roy?
Put a parentheses of mostly qualified.
Oh, because sometimes you have a strong line of sight term that's different from most of the multipath, and therefore you get a Ricine population. And so when you look at the statistics, there's a mean, and then there's a zero mean complex Gaussian process on top of it. So I'll get to the Ricine case later. Okay, now if the receiver is in motion, so that there's a starting point x0, but then there's motion of the receiver with a velocity v, then x really becomes that x0 plus v times t. And so you can write that g is a function of t, given by this, but now h is a function of t. So that's where you get time variations for the most part in wireless channels. It's from the motion of a terminal at one or both ends that by changing space, therefore changes the path gain. So it's not really a temporal thing, it's a spatial thing. But it turns out to be a temporal thing if you're moving. So that should be clear, yes? Yep. Question? What are you doing right now?
So at a given x, given location, is it possible to estimate accurately the in-phase and quadrature phase components of that complex Gaussian? Or does it depend upon the local oscillator at x?
At a given point, you can definitely measure the in-phase and quadrature component of H. Now, if you want to get the statistics of the in-phase and quadrature, then you have to sample all around that.
No, I don't mean the statistics. The actual value at a given point in time at a given point in space.
Sure.
You want to estimate it from the transmitter to a given point at the at the receiver.
Right.
Is it possible to get the actual values of the real part and the imaginary part, or can you only estimate the amplitude?
Oh, okay. So can you measure both in-phase and quadrature, or can you only get the amplitude? Transmit a sine wave and then lock onto it at the receiver, and now you can demodulate the signal into an IAQ.
You would need to know the phase at the transmitter.
Well, okay, now, you'll get IAQ within a phase constant, so that relative to the actual transmitted signal, there may be a phase shift. So you get it within a phase shift. If you want to get it exactly, then you have to use a cable like in a network analyzer. Okay. Any more? Okay, so I'm going to tell you some things about the path gain and then about H, because this is where we split into the large scale and the small scale. The so-called path gain, there's another point that I want to oh, I get to it later. Somebody should ask me how do you take into account other frequencies? So far, I'm only talking about a single frequency. And so is a path gain something that applies at one frequency and it's different than another? So I'll get to that in about 2 slides. The path gain varies slowly over space and therefore over time, assuming that there's mobility. What I mean by slowly, I'll get to, but it also changes slowly with frequency. That is, it's not randomly changing from one frequency to another, but it does so slowly, usually not changing much from one band to another. So think of a band as 100 megahertz. So in 1 megahertz band, you're going to have pretty much the same path gain throughout. Slight difference, but not big. It's only as you start to move hundreds of megahertz or gigahertz away that you might see a change in G. The spatial changes in G are due to spreading of the transmitted wave. You know, there's like 1 over r squared in free space propagation. So if you're at some distance, a kilometer away, and now you move 2 kilometers away, r squared means that you changed by 6 dB. So that's a big change, but it takes place very slowly. It takes 1,000 meters for that change to occur. So that's one change in G, and there's another one due to structural variations, which is called shadow fading. That is, if I'm on a city block, and my path to the transmitter is affected by the local buildings, that's going to be true for quite a while. But if I move to the next neighborhood, different buildings in the way, different buildings in my surrounding, I'm going to experience a different path gain. So that's the kind of variation that occurs over tens or even hundreds of meters. So that's what I mean by slow variations in space. It takes tens or hundreds of meters to see a change in G. Yep.
So
Michelle?
for the UWB signal, whose band is very broad, and when we talk about the dependence of the path gain on the frequency, so how do we characterize the channel model for the UWB signal, or we do not need again model?
So I think your question is in the case of ultra-wideband, where you have much larger frequency variation across the band, what happens to the notion of path gain? That's actually a good point. In the earlier versions of ultra-wideband, they were actually baseband systems that went from almost exceed gigahertz. So in that case, path gain didn't mean much. It was hard to define because it's so different at at very low frequencies and also at microwave frequencies. So it was meaningless. The later versions of ultra-wideband are really bandpass systems centered on like 5 gigahertz with plus or minus 2 gigahertz of bandwidth. So that the relative variation there is much milder, going from 1 to 7. So you can define a path gain as being the path gain is frequency.
Piecewise.
Yeah, or no, just pick one in the center, and then you can reasonably assume, especially if it's going from 4 to 6, that it's not much different at 4 than at 6. So you choose it at 5, define it there, and let it go with that. But for the baseband type ultra-wideband, you're right, path gain is kind of hard to define. So I think I covered this. Do you get the idea that what we mean by large scale? Now, small scale is actually more interesting. The variation of H over the terrain, over the local environment, is due to multipath, which is the scattering from structures in the environment. The variations over space are fast. That is typically on the order of a wavelength or less, and that's why it's called small scale fading. At 2 gigahertz frequency, the wavelength is 15 centimeters. So on the order of 10 or 15 centimeters, which isn't very much, you get a complete change in the response of a receiver to a transmitter down the way. Right? So that's small scale. And it's because it changes so rapidly in that distance that you can do some local averaging and pick up all the random samples of the gain and get an average for the squared magnitude. There's also a fast fading over frequency, and by that I mean you don't have to go tens or hundreds of megahertz to see a change in the path in the fast fading path gain. It can be on the order of megahertz or a few megahertz. So on a 20 megahertz channel, as in some wireless LAN bandwidths, you can see quite a few variations, a lot of frequency selectivity over that band. So that's what we mean by fast fading in the frequency domain. And I say the scale of it depends on something that we call the RMS delay spread, which I get to later in the talk, which may be in the second version of this. And finally, there can be fast fading over time. If you're moving through the environment, you could experience what seems like pretty rapid fading. For example, at 1 gigahertz, if you're moving at 60 miles an hour, I think you can see changes on the order, rapid changes on the order of 100 milliseconds, 10 milliseconds, something like that. So that's fast fading over time.
That comes because you are random, very fast sampling different spatial moments.
Yeah, the reason that you're fading over time is because you're moving over space. So we should always think of temporal fading of this kind as being related to spatial variations, not as being due to actual time. Sometimes when you stand still, there will be temporal variations, and Ozga, among others here, has measured some of that. Just because things are moving in the environment, or even fan blades turning. Giovanni, you're an expert on that, right?
I'm here.
Yeah, right? Because you ran into that in the shelf tag
That's right.
research.
I was puzzled for a couple of days as to what was causing the frequency shift.
Right. So, right, so you can have motion in the environment. The biggest cause of motion in the environment, of course, is you and all your other fellow humans. It's people moving in the environment that probably cause and doors opening and closing. But that's a totally different thing, and we're not going to talk about that. We're talking about motion-induced time variations, and it's really because you're moving over space, and space is causing variations. Okay.
Larry, there is one more effect, Doppler spread. So just because of the blue or red shift depending upon where you look at your angle relative to the transmitter, and all the scattering of the environment around you can cause the third component of time variability.
Well, but I think I'm going to talk about Doppler later. But I think of Doppler as being a frequency manifestation of the temporal variation. Obviously, they're duals of each other.
Because the other one is like, as you said, is when one moves through the space,
Yeah.
actually the new scatterers come into the picture and all scatterers disappear. So it's like, because Doppler, Jake's model assumes that the scatterers actually are still the same.
Coming uniformly from all directions
Yeah,
and staying the same.
And staying the same.
Yeah,
In reality, it's
Yeah. Within the scale that G stays fixed, you can make an assumption like that. It's a convenient assumption. If G changes, that means the scatterers have changed, and therefore you have a different picture and a different H of X. Okay. So,
Larry, the locality of 10 wavelengths, is that for H of X?
for we get H of X.
Based on the locality measurements of 10 wavelengths, is that the way we think about it, or is it G? You were saying average over, to get the Rayleigh distribution, we
Yeah.
average over 10 wavelengths.
Well, the reason I say 10 wavelengths is not because the environment changes after that. It's that that's all you need to get a number of independent samples
For H of X.
for H of X only.
Right, and then if you move that center by half a wavelength, you get a new, you get a change.
Yeah, you get a change in H of X, but it'll still be part of the same statistical population.
Right.
Now, if you then move 100 meters away, you may have a different population of samples, and maybe the same distribution or a different one, but it's coming from a different.
But the change might be significant if you stay fast, right? Even though you sort of take an average over 10 wavelengths and shift to the center by half a wavelength, or
I'm missing.
like if the way I think of it, you say that H of X will change with half a wavelength.
Yeah.
Of,
Right.
and I'm thinking, okay, I'm taking this 10 wavelength circle and I'm moving it by half a
Oh,
wavelength.
you're moving the whole circle.
Right.
Oh no, you're still in the same population.
Yeah, that's why I'm saying. That's why.
Well, no, but that in fact is a key point. Think of a circle, and over that circle you have a certain population of points. Let's say they're Rayleigh.
Right.
Now you take that whole circle and shift it
By half a wavelength.
half a wavelength. You're going to, of course, every new sample that you introduce by shifting it will be another independent sample from that same population.
Right.
But the population of the new circle will be statistically the same as the population of the old circle. If the population itself changes, it's because you moved tens of meters away.
Right, so there won't be much change.
Well, there'll be changes in the global average, the average over the circle. That will change as you move further and further away from the original circle.
Right.
Correct, it's the same Gaussian distribution.
No.
You shift it, so it's translationally invariant random field. So
No,
of
no,
course the
I
mu
understand.
will be correlated with the wall.
Right, that's what I'm saying.
Yeah.
So, I'm trying to understand what fast means.
Frederick, I think the distinctions between the statistics of the entire circle, which doesn't change much when you move the circle a little bit, but an individual receiver at an individual point does not sample the statistics, samples just one point within that circle. If that individual receiver moves to a point that is even half a wavelength away, it's sampling a different point in that population. And from the point of view of that receiver, the channel has changed dramatically.
That I understand completely, right? What, the way sort of like connected here is I'm thinking of HFX as being obtained through an average.
Oh, no, no,
But the
no,
receiver
no,
cannot
HMX
do
is,
that. The
HMX
receiver-
is a point property.
Okay, okay. Now I understand. What you're saying is the statistics is obtained.
Yeah,
Okay.
right.
So an over 10 wavelengths
That-
is just
that-
decorrelation.
that I
It's
understand.
essentially decorrelation.
But maybe I missed
I
something.
told you the faculty was here to help.
So all these things that you say, the variations are fast and, you know, everything. So for different frequency, this definition of fast will be different, or are they exactly the same?
So the question is fast and slow different for different frequencies? Short answer, yes. Because, well, fast depends on the frequency. Because when your wavelength is, let's say, 15 centimeters, you only have to go 7.5 centimeters to see a big change. But if your wavelength is 100 centimeters, you have to go 50 centimeters to see a big change. So yeah, fast and slow is frequency dependent. That's good. Did I say everything I want to say here? Yes. Okay. So now I'm going to actually define path gain and even get into describing models for it, at least on a superficial level. So G is the received power divided by the transmitted power. That's simple enough. PR over PT. In making this definition, we assume omnidirectional transmit and receive antennas. And we assume that this is generally a decreasing function of distance, and that's because of spreading of the wave as it moves away from the transmitter. On a line of sight or LOS path in free space, this is the formula for G. It's the square of lambda, the wavelength, divided by 4 pi times the distance. And that's called the free space path gain. The reciprocal is called the free space path loss, or we can define it in dB terms as follows. It's minus 10 log G, or minus the dB path loss. That's the usual definition of path loss that people use and that we'll discuss. So, I go back to something I said before. This is not as simple as it looks. Because of multipath, G can vary with frequency over the signal bandwidth and also with spatial position over very short distances. All right, we've already discussed that. So for which frequency and position are G and path loss defined? And that's where we get to the averaging. Typical averaging over plus or minus, here I say 5, plus or minus 5 lambda of the nominal position. If you can average enough samples over that space, and you can get an average of a good approximation to G. So at 2 gigahertz, where lambda is 15 centimeters, you would average over a circle of radius 75 centimeters, which is not even 2 square meters. And that would be sufficient to get a local average. I've said this before, the local spatial average is pretty much independent of frequency over a typical signal bandwidth. So if I go back to PR, this guy up here, the way to define him is as the local spatial average of the received power, not the power at a particular point, but averaged over the local environment. And this averages out the spatial variation due to multipath. Now, show me by raising hands, how many people here understand why you get this variation over space when you're in the presence of multipath? Do you understand the concept? Giovanni, put your hand up. I know you don't understand this. Okay. So some of you do and some don't. I'm going to explain it very simply now, and I'll get to more mathematics later. If I stand here and I get reflections from the walls, I'm going to get an echo from many different directions, maybe a large number of echoes, and they're all going to have an RF phase, right? And they're going to be in some relation to each other, the result of which will be that they'll either all add up, or they'll all cancel each other, or they'll be somewhere in the middle, right? Right now I move here half a wavelength away. All the phase relationships change. Not just that each one changes its phase with respect to me, but with respect to each other. So all the phase relationships have changed in just a half a wavelength. Now they might reinforce instead of cancel, or cancel instead of reinforce, right? So that's why you get the spatial variation. It's a matter of sum of phasors. And in a rich multipath environment, you have lots of phasors, and that's why you get multipath fade. Okay, so there's an interesting result that comes from the spatial averaging, and that is that you can measure the path gain and convert it then to path loss using a single frequency or CW signal sent from the base station or access point. So you don't have to measure over a wide bandwidth in order to measure the path gain. You can just...
So Larry, whenever we want to measure PR, we should always keep averaging. Is that how it is done, or?
No, I'll get to that in the next slide. You don't have to move in order to, you don't have to, but you can. In cellular, they do this a lot with cellular drive testing. They transmit a pretty narrow band signal, and the van moves around and makes measurements. And it measures received power at short spatial intervals, and then averages over 10 lambda or more to obtain samples of G. So that's what we've been talking about. But Chandru says, well, but, you know, do you have to move in order to measure it? No, you have another way out because of the variation over frequency. And that is fixed paths. You can measure in a given spot by using a swap frequency transmitter and a wideband receiver. That's the other way you can do it. Because I mentioned that you get a frequency selectivity. If you measure over a large enough bandwidth, you'll get enough independent samples over frequency that you can do it that way. It's the dual of the spatial variation.
Excuse me, Larry, but are they really mutually ergodic? Is it the same thing to average over space? I mean, is averaging over frequency at one location is truly equivalent to measuring one frequency over a ring of 10 lambda locations? I mean, that's not obvious.
I say yes. What do you say?
I say don't know.
Okay,
Because
this is a democracy.
non-obvious.
Let's have a show of hands. It's a good question. I mean, I've never seen a formal proof of that. Or if I did, I forgot it. But my feeling is that here's a test. If you took samples over a large enough frequency interval and computed the population, it may not be Rayleigh or Ricey, and it may be something else. And then you did the same thing spatially around that point at a single frequency, would you see the same population, the same probability distribution? I think you would.
I'm afraid it might be average temperature over hospital.
I think the key is in what you said in the previous slide. It has to do with the RMS delay spread. If the RMS delay spread is many, many periods,
Yeah.
then let's say there's 100 periods of the 100 lambda between the one echo and another echo. You change the frequency by just 1%, you've mixed up all the relative phases. So in a situation where the RMS delay spread is small compared to the period of the signal, then
What are you calling the period? We're just setting the probe.
let's say you do it at 1 gigahertz.
Okay.
The wavelength the period is 1 nanosecond. If the
Oh,
delay spread is like
okay.
5 nanoseconds,
Uh-huh.
then in order to get that other sampling of the distribution, you have to change the frequency by 20%.
Yeah.
That's a lot.
Yeah, right. True. Right.
So it all has to do with the RMS. I mean, the answer to Leo's question is,
Right.
if the RMS delay spread is much larger
Yeah.
than the period,
Well, that's certainly true. You need enough independent samples in order to realize in the frequency domain what you can realize with the spatial sample. Right. And that's related to the RMS delay spread.
I think those are the two elements. Another element is that when you do spatially, that you really get the same population. If the population changes within your circle, then things are not. You don't get a same. If you change it by 10 lambda, if you get the same reflection
Oh,
sample
yeah.
at all points.
Yeah.
If now you get, at some other, 10 lambda away, you get completely different population.
Right. So what I think is roughly equivalent is if I stand in one spot and measure over a very large bandwidth, I'll get the same population of samples as if I move from my center point to different points in my own circle.
Right. But if that assumes that you get essentially the same population of reflections when you move up.
Right. Well, if I move and I get a different population in space,
I mean,
I'll probably also
statistic-
get a different population of samples and frequency.
Right.
I think the simple back of the envelope model to describe what you just said is this. If I'm at a given location, I'm measuring the power, it is partial contributions from all those receivers. What I'm really interested is the sum of energy, so the sum of squares.
Right.
But here, because I'm getting all these partial contributions with different phases, and when I square it, I get a lot of cross terms, which are particular to this term. So I would like to kind of average these cross terms out. It doesn't really matter how exactly I approach them. If, for example, as Giovanni said, by changing the frequency, one can make the relative phase combinations to go over the full circle to pi, then on average all these cross terms will disappear and I will be left with the pure sum of squares of diagonals, so it will be just local energy. Or alternatively, I can break this Ferris relationship by moving around. So and then cross terms will disappear again. So yeah.
So we're
Now
close.
now I understand.
Now that you've explained it.
Yes, that's exactly how it's derived in Rappaport's book.
Oh, really?
You have to get rid of the cross terms.
So Rappaport is.
Or you have to read the Rappaport's book.
He beat you to the
Before
punch.
asking the question.
Okay. Right, so Chandru said, what if you can't move? And the answer is, you can do it by sweeping over frequency. So you average over frequency instead of space, and you can do this by sending a broad probe and then using a spectrum analyzer at the receiver, or you can use a vector network analyzer, VNA, for the whole TX RX pair. And these are the kind of measurements that are often made for environments like this, indoor environments for wireless LANs and other systems.
Suppose you have a transmitter at some point and you're able to observe the variation in h of t as a function of, h of x as a function of x in some other area.
Yeah.
Now if you change this transmitter from being omni to directional, is there some simple way to understand how the variation with x changes at that place?
So it becomes directional, but is it still beaming in the direction of the original circle, or is it?
So earlier it was omni and there were whatever reflectors there were.
Yeah.
Now it's directional and it's pointing in some particular direction.
Okay.
As against to all the other reflectors. So how does the variation in space change?
Oh, I see. And there, all right, so Suhas is raising the point that if the transmitter becomes directional, it's not going to illuminate all the scatterers the same way it did the first time, when it illuminated them all equally. Now it's sort of
It's
being
not
selected.
clear if it's actually illuminating all of them or not. It might illuminate them indirectly after reflecting the first surface. I don't know how it changes. That's my question. How
Okay.
does
Again, these answers are always going to be fuzzy, but it's sort of like this. If the beam of the now directional transmitter is still large enough to hit all the main scatterers, pretty much as it did before, then you'll get pretty much the same population of h of x in the original circle. But if it becomes so narrow that it hits some of the main scatterers more and some of them less, you're going to get a different population.
But does the rate of variation with space change?
Will it change the spatial variation of the large scale fading?
Yes.
Yes, it'll change the large scale fading because.
Oh, I'm sorry, the small scale, not the large scale. The small scale.
Oh, will it change? You'll change the small scale fading. It may still be complex Gaussian. It may still be Rayleigh faded amplitude, but it'll be a different magnitude, a different mean squared value, and you'll have a different statistical set of samples.
And will one be necessarily faster than the other
Fast versus slow.
in space?
I think fast or slow will still be determined largely by the wavelength, and not by the shape of the beam. now we're getting closer to an actual model. This is a way that you can define the path gain. And we do a lot of things for convenience, not because it's fundamentally true, but because it makes it easier to do the engineering. A good way and a widely used way of modeling the path gain is to say that it's some function of distance, d, times s. And I'm going to explain what s is. Fd is a median value for g over many locations at distance d. So imagine that I'm the transmitter and I find a circle of radius d, and I measure my path gain to each point on the circle, 360 degrees. Will it be the same everywhere on the circle?
Depends on the environment. Depends on the environment. If you have a lot of buildings, then it will be.
Yeah, depends on the environment.
But in free
If
space-
we're in free space and there's nothing around, then the answer is yes. But in a wireless environment, that's almost never true, and therefore, we're going to see a different story at each point, and therefore, there's not going to be one value for f, for g, but there's going to be a median among the population of values. There's a median, and we call that f. And then the variation about it, the RMS deviation about that median is related to s. So s is just the difference between the actual sample at a particular point and the median over all the points. Right? Just a convenient way to express it. F depends on the antenna heights, the wavelength, the type of environment, and so on. As you say, it'll be different if there's no scatterers or structures in the environment.
Larry,
Yeah.
you could ask a really dumb question. Why medium? Why not mean?
Because, as you'll see, in fact, as you already know, the median in the linear domain becomes the mean in the dB domain, which is really where we want to operate. So we can define path loss as minus 10 log g, which becomes minus 10 log f, plus 10 log s, or something that I call the median path loss plus some other term s. Right, so that's clear enough. We can do that if we want. In commonly used wireless terminology, this is referred to as the path loss, as opposed to the median path loss. And S is referred to as shadow fading. And I claim, and it doesn't matter if you agree with me or not, but I claim that these are both misnomers for reasons that I will now explain. I say the path loss at a given position is the total dB loss of signal. The receiver doesn't care what the median is at all the other points in the circle. It only cares about its own measured power. So it can't separate the median from S. All it knows is it gets the sum of the two. So I think path loss should be used to define the sum of the two and not the median. But in the literature, you'll see path loss constantly defined, and the author really means the median at that distance over all possible locations. All right, now this is called shadow fading. And I claim that that's a misnomer also. It came out in the early days of cellular because there were shadowing buildings in the way of between the transmitter and the receiver. And so it's natural to call the variations that you get about this nice straight line shadowing, but it may be due to blockage by other things besides blockage by physical structures. I'll tell a brief anecdote that Giovanni will enjoy. Back in the late 80s, some colleagues of ours at Bell Labs measured urban microcells, where you had a transmitter on Lexington Avenue in Manhattan, and another van moved down the street and made measurements all along Lexington Avenue and collected tons of data. And then in the summer of 1991, a young grad student came to work with me at Crawford Hill. She didn't know a thing about wireless. Her name was Andrea Goldsmith. She's learned a lot since then. But Andrea spent the summer working on this data and doing this, this least squares fitting and finding the median and the standard deviation. I remember in the street, there's no obstruction. There's line of sight all the way. And yet, Andrea's data showed a nice straight line because she did a least squares fit, and there was a lot of fluctuation about it. And it wasn't shadowing. It was due to the fact that in different parts of the street, you have different structures adding up in different ways, even when you average things out. So shadowing is a misnomer in that sense, but it's a convenient one. We call it shadow fading. Everybody knows what it means. It's the variation about the straight line of the measured path loss. Okay. So here's how we separate out the median and the shadow fading and characterize them. You measure path loss over a coverage area at many positions and you form a scatter plot. I'll show you one in a second. I'll show you one. This is a scatter plot of path loss versus distance at 1,500 locations. Okay. Then you choose a functional form for the median, and this is a popular one. It's A times D distance to the minus gamma, where gamma is called the path loss exponent. And then you do least squares fitting of this function, so you find A and you find gamma so that you get a least squares fit of that function to the scatter plot. So that way, the median is just what you get from the least squares fit, and then the deviation from that is what you call the shadow fading. So let me show you that picture again. So here's a scatter plot, and you can put a straight line through that that's got the least square deviation about it. So this dark line is the median, and deviations, that's the shadow fading. And this was done by Saeed Ghasemzadeh, who works at AT&T Labs with Leo. He did this for many locations in many different homes. And this is a scatter plot for one home. And when he takes all these deviations and puts them into a population and then plots their cumulative distribution function, we find that on a distorted scale that's designed for normal or Gaussian processes, comes out a very straight line. So the upshot of this experiment is that the shadow fading, the deviations, S, are normally distributed. And this, in fact, has been found for all kinds of environments over all kinds of measurements over the years. Is that a question?
So what the physical mechanism will occur that the shadow fading when we count its dB is always zero mean?
Why is the shadow fading always zero mean?
Yeah, in taken.
What's the physics?
It's a consequence of your fitting. The way you do least squares fitting guarantees that the solution will give you a zero mean. Okay, so if it didn't, then just a shift in your curve would eliminate the mean, and you'd have a better least squares fit. If you're really getting least squares fit, it means there's no bias.
Okay, so when we try to get a number of data, we can try to get order to get the factor. We sort of impose a constraint on S. It has to be zero.
Yes, in essence, by doing the least squares fit, you're imposing the constraint that is zero.
But why don't you do the fit in power?
Instead of in dB.
Instead of log power.
Because there's, maybe starting with free space propagation, there was always this bias that you had basically an inverse power law.
Okay,
And
so
if
you're
you have an
looking
inverse
for
power law, it won't be nicer than
a
the
log
linear.
curve.
Yeah, yeah.
Right, so you're fitting the answer in you're putting in an assumption of a power law
Yes.
distribution. So if it's a power law distribution, you get a nice fit this way.
Exactly.
Okay. And the second question would be, this all includes the ground bounce interference.
Oh, yeah.
It shows up in the statistics, basically.
Yes, the ground bounce and every other bounce shows up in the statistics. But if you had only, let's say, line of sight and a ground bounce, you wouldn't get a nice fit like this. So it's usually in a much richer environment of scattering that you'll get something that looks so nice. In the single ground bounce or line of sight plus ground bounce, it won't work.
At some point, I want to ask you the inverse question: is if you put your antenna underground, what happens to your distributions? Have you ever looked at that?
What does that mean underground?
Well,
You dig a hole, you put it at the bottom of the post. Les is here from Fort Monmouth, and we're actually looking at the issue of the distance distribution if you bury an antenna underground. I would guess it would be biased towards a beam going up, but I wonder if you
I
had seen
think
that
your path loss formula is going to be strongly dominated by attenuation.
as you go out.
Yeah.
Rich,
So, yeah.
are you getting a Nobel Prize? I think it's a known fact already. These two gentlemen from Bell Labs, that's exactly what they did. They took big antenna, put it really deep under the ground, and were rotating it any way they can, and then they saw this background radiation, which was always there.
That antenna wasn't in the ground.
I think it was.
No, it was right on top of Crawford
No, it's
Hill.
like Crawford Hill, it's a big horn.
Was it? Yeah.
But no, this was a
The thing is
low.
a neutrino experiment.
Well, I thought I read it.
The Crawford Hill
In
black body
Wikipedia.
experiments were above ground. Twice. Okay.
Leo, I'm trying to talk about propagation, and you're talking about the creation of the universe. I mean, let's stick to the subject. All right. So this is a very interesting result because it says, yes, you can do a least squares fit, and what you get for the deviations about it will be kind of Gaussian, and that makes modeling easier. I mean, the name of the game here is how can we devise a model that works in all kinds of environments, and we just have to find different parameters for different environments.
Larry, this is for a wide range of frequencies. As you said, it is a model with for a wide range of frequencies, right? And for example, in the spectrum of electromagnetic spectrum, it is for the whole RF band. These models are true. Or in the electromagnetic spectrum, the whole of RF band from, for example, hundreds of megahertz to gigahertz.
Okay. Would this be true in a very wide band? No, I mean, almost everything I say from here on will be true for narrow bands, relatively narrow bands. As soon as you talk about the...
No, relatively narrow bands in the whole spectrum.
Yes. I mean, it's for these kinds of environments, wherever you are in the spectrum, you can make a statement in a model like this, but the parameters will be different from one kind of frequency range to another.
So my follow-up question is, when does this ray model fail? Basically you are actually approximating a wave model to a ray model. When does it break these kind of models? It's more of a physics question. Like basically these are waves, and we are approximating that those are rays as rays. Aren't we?
I'm just in the shop.
Basically these are electromagnetic waves, basically, and they are all adding up in
Yeah,
phase and all.
right.
And these, when you get these graphs, you model this as, like, for example, he told ground bounce model and all these things. Those are ray models, right? He assumed.
Ray tracing.
Yeah, but all right. Keep in mind that in most of these environments, you have a lot of rays, and no one ray dominates unless it's maybe a line of sight. So,
Actually, Larry, the ray model is correct at any frequency as long as you do the integral, including the phase. It's called the Huygens principle. The ray versus wave duality is only a problem if you look at if you don't keep track of the phase.
That's all.
okay, so now we want to look at the median path loss, f of d, and what's a good model for it. And I said before that this is a good starting point, and it starts to be very popular the more people measure in the more different environments they measure it in. So in dB, that means that the path loss is some constant plus 10 times some other constant times log d, where in that formula, big A and little a are related this way. But there are variants. I mean, this is the simplest version that you can think of. There are variants. For example, there's some models that use multiple slopes. That is, in one section you've got one gamma, and then there's a piecewise continuous segment following it that's got a different gamma. So it's got one slope, and then it's got a steeper slope. That's a segmented model. Or in some cases, like in indoor environments, where you have walls that cause attenuation by exponential decay, you would add an exponential term to that original term to account for losses through the walls. The most famous of the path law models is the one by Hatta and modified by Cross 231. The Hata model is based on an extensive database of Okamura. He made measurements around the entire city of Tokyo in the late 60s. And Hata took it all and reduced it and got a nice, fairly simple way to characterize A and gamma for different heights and frequencies. It was good for frequencies up to 1.5 gigahertz and also large cells. COS 231 is something that was done in Europe in the 90s to extend the Hata model to a higher frequency, 2 gigahertz, and also to smaller cells. Here's my favorite model. This is work I did with Vinko Ercik back in the 90s for 2 gigahertz and suburban macrocells, based on a ton of data that people had collected at AT&T Wireless Services. It's basically the same as this, except it's kind of a two-slope model. Out to about 100 meters, it follows free space path loss. And then beyond that, it takes on a different gamma. And gamma might be as low as 3 or as high as 6. And one of Erceg's big contributions was to recognize that gamma is just a statistical parameter that fits a particular environment. There's nothing physical to justify it. So if you measure in one cell and you do the least squares fitting, you'll get gamma of 3. You go to the next cell and it might be 4. So we decided that the way to treat all this was to treat gamma as a variable that's changing from one cell to the next. And he had enough data that he could actually come up with a probability distribution for it. Gassim-Zada took that same idea and applied it to the ultra-wideband environment that he had measured in various houses around New Jersey. Similar to Erceg Greenstein, except that the model parameters are different. Okay, now I'm going to say a few words about the shadow fading itself. It's zero mean, it's Gaussian, it's a random variant over the coverage area, it's got some standard deviation sigma. And again, sigma is whatever you compute from your least squares fitting. There's no theory that explains what sigma should be. But experience shows that it ranges from 4 to 12 dB depending on the environment. Lower values in indoor environments, larger values in outdoor environments, especially in big cells. Typical value for cellular is 8 dB.
So why does outdoor have more shadowing than indoors?
Yeah, why do outdoor environments have more shadowing? I think, but I'm just kind of speculating here, that the outdoor environment is much more irregular. It's irregular. You have tanks, you have cars, you have buildings, you have all kinds of objects that sort of change in one part of the environment to another. Whereas indoor, things are sort of regular and well behaved.
No, but indoors have more absorption, I thought, because the walls and these steel girders and everything, those could have more absorption.
You don't get much absorption. You're talking about indoors? You don't get, it's more reflection and transmission. There's not a lot of absorption in walls. But again, the answers like this are always fuzzy. I think it's because outdoor environments are more unpredictable. And you get more variation over a large area.
I'll comment, sigma is the variation in absorption, not the actual absorption. Indoor, you have less variation, not so much less absorption.
In the Erceg model, and also the Gassim-Zada model, sigma is treated also as a random variable from cell to cell, not just gamma, but sigma. Now, if you go along a particular path and you actually make your measurements and later do your curve fitting and find that S varies along the path, it's got a certain spatial correlation distance over which it's basically the same, and that's called X sub C, the correlation distance. And it ranges from 10 meters in microcells to 100 or more meters in large cells, depending on the environment. Years ago, a guy in Sweden measured the autocorrelation function of this quantity, S as a function of distance. And he came up with a sort of result that said it was a double-sided exponential. And people have been using it ever since, partly because it hasn't been measured much anywhere else, and also because it's such a convenient description for the autocorrelation function. So
Where were the measurements done? I'm curious.
I think he did it in Stockholm.
Like cellular
Yeah, cellular, but in a city.
and
Yeah. He might have even done it in a few cities or in a few different areas, because I remember that his results showed different values for this correlation distance depending on whether it was urban or suburban. So he probably made a few measurements.
Because I think this is one of the very important things to know for like a sensor.
Yeah.
But
Right.
he probably, his results probably don't apply there.
That's a good point. Predrag's saying that it's important to know the spatial properties of S for sensor networks, but also it's probably true that a result like this for cellular doesn't apply to sensor networks, and therefore there's some important information missing from the literature and from the
So
field.
who's gonna do this research?
We could use it. We were looking for sensors that are in the ground, and they're going to have a very different distribution here. And antennas that are not going to be up on tall towers. Generally, sensor networks are not going to have that.
Yeah, sure,
the
that's why it's
height advantage. You're going to be working near the boundary
Exactly.
between the edges of buildings, the edges of the ground.
I think that's your point.
It's going to be very different.
Right.
We certainly could use that information.
Okay, so it's a little bit after 3. I have two choices. One is to stop here and to resume hopefully sometime in November when I get back here, or to go 3 more slides so I can introduce you to Doppler and Rayleigh and Ricing. Who wants to walk out of here knowing more about Rayleigh and Ricing and Doppler? Well, you already know, so you can't vote. Only students vote. Nobody over the age of...
Be careful about that.
I'll take back the question. Students vote. Would you like to stay for 3 more slides? And- and-
Yes.
All
I
right.
think 30 divides all the students.
What, Ron?
30.
You mean you stop learning once you're 30?
Yeah. Crazy.
I enjoyed the day that I get to be 30.
Ah, yes.
So I think it's-
It's a good reason to move to Mars.
Yeah, right. It's only true on Earth.
I'm 29.
Okay, so I've told you everything that I'm going to about the large-scale variations. So everything from here on is about the small-scale variations, the things having to do with multipath and scattering in the local environment. And the first thing I want to introduce is the notion of Doppler frequency. You probably all know this from physics, so it won't hit you as something too new, but think, you know about Maxwell's equations and plane waves radiating from a transmitter. So think of this gray rectangle as really being just a portion of a plane wave that's radiating in the direction from the origin outward, and it's moving in this direction. So relative to my arbitrary x-axis, it's making an angle alpha. Okay, alpha can be anything. Over here at x0, y0 in the xy plane, I have a mobile and it's moving at velocity v, and it's moving in the x direction. Okay, so now this E field is moving this way, and it's got unit amplitude and it's got some phase, and the phase is of course 2 pi times the carrier times time, and as it moves along the ground for each x and y, it's got an additional phase term that's related to x cosine alpha, y sine alpha, and so on. So this is just trigonometry. You can convince yourself that is true. Now, at t equals 0, the mobile is here, but it starts moving in a direction with the velocity v. So as time moves on, its position is changing, and so the phase is going to change slightly as a function of t, and it's going to look like this. And I just regroup things so that the t would be all in one place and all the t independent terms would be in another. Because the frequency at any one time is just 1 over 2 pi times the derivative of the phase. And so what we see is that we get the original carrier frequency plus an additional component due to the fact that the vehicle is moving in space relative to the wave that's impinging on it. This is the Doppler frequency, which you've studied in physics, and you've seen it in acoustics and also in electromagnetics. So what you see here is that it depends on the wavelength, it depends on the velocity, and it depends on the direction angle between the motion of the mobile and the direction that the wave is coming from. Okay, so that's Doppler, and you all know what it is. But now we get to the impact that it has. So now, let's take a top view. Here's our mobile moving, and he's got rays coming at it from all directions, right? This, in fact, is the original Jake's view. There you had uniform angle of arrival from waves of roughly equal amplitude. Okay, so let's say that there are n rays, and they're coming from all these different directions, alpha 1 through alpha n. And so the corresponding Doppler frequencies would be V over lambda times cosine alpha 1 all the way out to n. So the received signal is the sum of n sinusoids at slightly different frequencies from each other. The result is that the amplitude of the sum varies with time, and this is multipath fading. They're the result of local scatterers scattering objects in the neighborhood of the mobile, and it occurs in both directions, from the transmitter to the receiver, and from the receiver to the transmitter. It's the same in both directions. Okay, so that's all clear enough. And that gets us to the notion of Rayleigh and Ricean fading. So assume that the n rays are of similar amplitude with random phases. The sum will be complex Gaussian in the limit of large n. This is due to the central limit theorem with autocorrelation function A of tau. Does everybody understand why the central limit theorem guarantees us convergence to complex Gaussian? Is that clear? Yes.
This requires, though, that make the assumption that for each delay there are a very large number of paths coming through. Right?
Does this require that for each delay there are a large number of paths? No, it doesn't. If they were fairly sparse and spread up, but of roughly the similar size and coming from different angles, you would still get a complex Gaussian. You don't have to have a dense number at each path. Now later on, when we get to the uncorrelated scattering model and the fact that that you can write each what do I call it? Each tap gain as Rayleigh, then it requires that you have a lot of paths close together at that delay. But not for this. Here we're just adding them all up and looking at the total power. And for that, you don't have to have closely spaced echoes.
This is Gaussian in amplitude, not in power or dB.
That's right. It's, in fact, it's Gaussian, it's complex Gaussian. The real part is Gaussian and the imaginary part is Gaussian. Which means that the amplitude will be Rayleigh and the amplitude squared will be exponential. Oh, I said that, didn't I? The envelope of the sum will be Rayleigh, and which is why it's called Rayleigh fading, and the envelope squared will be exponentially distributed. Okay. Now this autocorrelation function, as you move along, you're seeing changes, and the question is, can I describe this in some statistical way? And the fact is, you can take an autocorrelation function, and that's what's called A of tau. And the important thing to know is that A of tau is related to the frequency content of your Doppler echoes, and they're in an interesting relationship.
I have a question.
Yes.
So why people for shadow fading they come up with that kind of correlation model, but for this A of tau, do they have like signaling model?
For this one, they have what?
Right, autocorrelation model like for shadow fading.
Oh, okay. So we're talking about autocorrelation functions. And Michelle points out that they use a double-sided exponential for shadow fading. And something else for this. Well, the reason they use it for shadow fading is because there have been very few measurements. And it's sort of like you grab at things that you wish for. When this one guy, Gutmanson was his name, in the 90s, published this model saying that the autocorrelation function that he measured for shadow fading was double-sided exponential, everybody jumped up and said, yeah, that's it, because that's the easiest one to use. It's just like, you tell me process is Gaussian, I won't even question it. I'll say, fine, I could use that. Tell me your system is linear, I'll say, okay, fine, it's linear. So, I mean, we're sort of like slaves of our convenience. And it was very convenient for me. Why is this different? This comes out of a theoretical result, which I'm going to get to the next time. The angle of arrival distribution determines the Doppler spectrum, and the Doppler spectrum determines A of tau. That's for another day.
Without mobility, so there is no time variation.
That's right.
But still, in the spatial really distributed.
Yes, but I think you were here when we talked about the Rayleigh distribution in that case being something that you could measure or realize in space around the point. But you won't realize it in time, you'll just get a constant signal. Okay, so Ricean fading is a larger family of which Rayleigh fading is a special case. So let's talk about that. Let's say there's also a dominant ray, much stronger than all the others. We said before that all the echoes were roughly the same and they added up in the central limit. This is often called the specular component, as if it came from a specular reflection off of like a metal object, as opposed to diffuse scatter. But it can also be due to a line of sight path. You can have a line of sight path, and then a line of scatter coming in much weaker, but all the same. So I'll get a dominant term plus complex Gaussian signal on top of that. Well, the envelope of that DC, that constant term plus complex Gaussian, has a distribution that was first reported by Steve Rice back in the 1940s. It's been called the Ricean distribution ever since. The only person in the world that never called it the Ricean distribution was Steve Rice. He was a very modest man who refused to name it after himself. But we know it is. It's the Ricean distribution, and it's Ricean fading. and the ratio between that specular term and the scatter power is called the Ricean K factor. It's just a matter of definition and convenience. When K is 0, we have a complex Gaussian with 0 mean, and therefore that's Rayleigh fading. When K is infinite, it means we only have specular power, one line of sight term and no scatter. That's the additive white Gaussian noise channel. So you can see that AWGN and Rayleigh fading can be thought of as just extremes of the Ricean distribution from K equals 0 to infinity. And I think, yeah, now it gets kind of heavy. I go into angle of arrival in Doppler. I go into multipath dispersion. When is it wideband? When is it narrowband? When do you get intersymbol interference? When don't you? Power delay profile. It gets really RMS delay spread autocorrelation.
It's only 10 slides.
Huh?
It's only 10 more slides.
Yeah, it's only 10 more slides.